Hey everybody, welcome to class number 2 of week number 15. So we've got PLC 15 this week, which is the set of practice problems. Answer 2 of them. There should be 2 multiple choice questions set up, so those are in the quiz format. And then homework 9 is posted, and that is a set of problems for you to do in order to get experience on the type of problems that we'd be asking for on the final. So it's for your practice, it's for your enjoyment, for your experience, not to turn in, just for you to do those, all right? And we'll be going over some of those probably tomorrow, and then I'll post a few more answers for them as time goes on. So the final is going to be a week from today. This is Wednesday, so we are looking at the final being in 1 week. And it's the usual deal where it will be available and you'll want to pick your time and get after it. So I also mentioned that there was a live on-campus review session that is on the Tuesday before that, and that's going to be in room 804 here at Cabrillo, 527. That's Tuesday, starts at 10 a.m. and it's in room 804. So if you are around that day and wish to do that, then by all means you're welcome. If not, that's fine too. In terms of what's left, that's pretty much it. We don't have much time to do other things in terms of assignments. So let's go ahead and continue talking a little more about lasers, and then we will move into some radioactivity today, and we'll continue that we'll continue that on Thursday as well, and that will be our final class session of the semester. So let's go ahead and start with the description of the solid state laser. Last time we talked about the helium neon gas laser, and essentially the workings of the helium neon gas laser are how you would describe most gas lasers. Okay, now I showed you the picture. I showed you the gas laser that we have here, or one of them, and it's it's about, well, not quite a meter long, but it's pretty big, and it's got the mirrors at both ends, and the laser light comes out, and all this stuff. The tubes in which the lasing happens are pretty substantially large. Okay, so then you might wonder, how do I go from something like that to something like this, which is simply a very easy device to click and to make laser light. Same properties of the laser light. In other words, it's coherent. It is a collimated thin beam. It is very intense, and it is essentially monochromatic. So we went through a couple of examples of some gas lasers, then the population inversion that we had going on with the gas laser. I had set up a hypothetical two-state system in which we had atoms in one level or another. So I'd like to just go ahead and finish that one out, and then we'll talk a little bit more about the solid state later. So here is a hypothetical two-state system. In other words, when we talked about the gas laser and the helium states and the neon energy states, we talked about how we had to excite the helium up, and then it ran into the neon, and then the neon decays. The neon gets excited, then it decays, and then it gets excited again, decays. So let's just look at a situation in which there are atoms which could occupy either a ground state or an excited state. And when they occupy the excited state, they drop to the ground state and emit a photon. And let's just suppose that when that photon goes by, it stimulates emission from the other atoms, and then for whatever reason we pump them all back up. Somehow we do that. All right. So imagine that we have these atoms here, and I drew this for you last time. The normal configuration would be one in which, suppose we have, say, 10 atoms. If we have 10 atoms, the normal configuration would be that these atoms are essentially all in their ground state here. 2, 4, 6, 8, let me make this a little bigger, 9, and maybe there's one in the excited state because the probability is not 0. This is the population inversion here. In which I have managed to put most of these up here in the excited state. And there's one down here because maybe it already decayed. 2, 4, 6, 8, 10. I got too many up here. Okay. So a population inversion is one in which they're all kind of ready, and it only takes one to drop spontaneously and then cause a stimulated emission of the other ones. So let's assume that we know what the energy difference is here, because, say, when this one dropped, when that one drops, it emits a photon. That photon has a wavelength which we can measure, and therefore we can know what the photon energy is. Now look, if we measure the photon wavelength and we know the photon energy, we know the energy difference between these two levels. Okay, so photon energy is equal to hc divided by lambda. So if we measure this wavelength, we know that photon energy, therefore we know what this energy difference is here, delta and E, between these two levels. Okay, so that would be the first thing. Or likewise, the opposite. If we knew that this level was, 2.5 EVs above the ground state, and this is where the lasing was happening, then I'd be able to tell you what the wavelength was. Same idea. All right, so let's suppose that this photon comes out and knocks all of these other ones down. So we get 9 emissions. Right, so the stimulated emission causes 9 more, well, I guess 10 total, right, because the spontaneous one counts too. But it stimulates all 9 other atoms to drop and emit exactly the same photon. Okay, so the stimulated emission happens of the other 9 atoms. That results in a total of 10 photons. Okay, so with the 10 photons, I know how much energy there is in the 10 photons, because it'd just be 10 times that photon energy. Okay. And it's 10 times hc over lambda. That's the total energy emitted. Suppose this is a pulse, right? This is an easy thing to think of in terms of a pulsed laser. Excuse me. So that one spontaneous emission causes stimulated emission of this population of atoms. They all drop, they all emit their photons, and then it takes us time to slowly get them up, put them back up, put them back up, put them back up. Okay, and therefore the laser pulse is regular in time. So we get one emission, all of a sudden all the rest of them cascade out, boom. There's an emission of a bunch of laser light, we take a little time. And then it happens again, boom, there's another pulse. Then it takes a little time getting back, boom, there's another one, right? So it's a pulse laser. In that pulse, we have this much energy. So if we suppose that For example, we could make it pretty simple. We could say the photon energy, suppose the photon wavelength was 124 nanometers. That means the photon energy is 10 EVs. And therefore the total energy is 10 times, this is in EV nanometers, and that's in nanometers. That's 100 EVs in one pulse. So there's 100 100 electron volts in one pulse of the laser. If that pulse happens in, say, maybe just say it happens within, a microsecond would be way too long. Let's just say it happens in a microsecond, but that's a ridiculously large amount of time for something like this to happen. Just because I want to be honest about it. Let's take a look and see if that can translate into a power. What would the power of this laser be if it imparts a pulse of 100 EVs in 1 microsecond? So let's suppose a pulse happens in 1 microsecond. Right, that's 10 to the minus 6th of a second. And therefore 100 EVs would be the amount of power. 100 EVs would be the amount of energy outputted, and that would be in 10 to the minus 6th of a second. So that this becomes basically 10 to the 8th EVs per second, which seems like a lot. Well, if I convert this into watts, into wattage, which I don't know if we've done before or not, but it turns out there is in 1 EV, there is 1.6 times 10 to the minus 19th joules in 1 electron volt. And the reason that it's that number is because that's the charge on the electron. The charge on the electron is the thing that tells us how much energy an electron picks up when it goes through a potential difference. Okay? Well, that plus the voltage. So if we do this and we convert that into watts, then we'll find that I need to multiply this. So I'm going to take the 10 to the 8th and 10 to the minus 19th. That's going to give me 1.6 times 10 to the minus 11. And that's going to be joules per second, which is that much wattage. Right, so this is a very low power laser, which probably should not surprise you because I only talked about 10 atoms decaying. If you want a substantial laser, you would need somewhere in the order of 10 to the 15th or 10 to the 20th of these things kind of happening at once. It should be a significant fraction of a mole, not 10. That's kind of a funny number. And a microsecond, like I said, a really long time. So anyways, that's how you can calculate the wattage of the laser. That's how you look at the population inversion, the energy differences, and so on and so forth. All right, so I want to go from the gas laser to the solid state laser. Now, there's not any difference in the actual laser light. The laser light is, like I said, has the same properties as the gas laser does. The wavelength might be slightly different, but we, as people who make these things, the wavelength, we can figure out, we can choose whatever wavelength we want now. Because the red laser and green laser were pretty easy to make, but the blue laser was terribly difficult to make. But now that it's been made, we can figure out how to do more of them. Therefore, I'll just give you a quick primer on the solid state laser. Not that there's going to be anything specific on this, but just to let you know how this works, let's talk about it. So essentially, it's based on the idea that when you put large numbers of atoms together, their energy states link up. So we've been drawing energy kind of ladders. We've been drawing the staircase energy level diagrams. Imagine that you drew one and then another one right next to it, and another one right next to it, and another one right next to it, and another one, and you drew 10 to the 24th of these things. The energy levels themselves would cease to be individually continuous. Okay? They would then become, they would cease to be individuals and they would become continuous. That's what I meant to say. They would stop being just an atom's energy levels and they would link up. This is the process known as hybridization. So when you're looking at energy levels in a solid, which has many, 10 to the 24th, 10 to the 25th worth of atoms in it, the states become a continuous set. All right. Now, we talked about the photoelectric effect already, and essentially, you can look at the photoelectric effect, excuse me, as kind of the opposite of a laser or an LED, if you like. Basically, how solid-state devices work is that we talk about a required minimum amount of energy necessary, just like we would for an atom whose electron is going to transition from a lower state into a higher state. There is a minimum amount of energy. In fact, I can't put in less than this, and I can't even put in that much more than this. Maybe there's another state up here I could put that much in, but I can only put in this much. And if I don't put in this much, then that photon gets ignored. Okay? And this is called a transparent material to that wavelength. And that's why glass is transparent to visible light. Maybe you've never thought about it in these terms before, but glass it's a quantum mechanical device, right? It's made of electrons and other stuff, but the minimum energy necessary to excite an electron in glass is on the order of 10 to 12 electron volts. That energy photon is ultraviolet. Therefore, it will absorb some of the ultraviolet that is incident upon it. But the glass electrons will look at the visible photons and say, those photons do not have enough energy to get us promoted into the first level state from our ground state, right? Into the first excited state. So they're going to ignore those photons. If I got a 10 eV difference here and I'm only talking about 2 to 3 maximum electron volts in visible light, that's only going to get you up to here. And so the glass just ignores those electrons. They just pass right by. And so glass is transparent to photons with energies that are less than their first excited state level. Now, when you look at a laser or solid-state light-emitting device, like a light-emitting diode, basically what's happening is we're causing electrons to drop through a known energy difference. So what we do is we take all of these atoms, we put them together, we make continuous energy levels, which are called bands. And what happens is you get situations where you have a band which might look like this, and then another band which might start here and go like this. And so what happens is the electrons are able to fall. That's an electron right there. The electron is able to fall through this energy difference and emit a photon. Okay? And because we can control the level spacing of these energy bands by technological processes I don't need to go into. So we can control this energy difference, and therefore we can control what the energy of the light is, and therefore the wavelength of the light that is output from this transition. That delta E we are in control of. So a solid state laser is essentially the same idea. This is basically just an LED. The diode is, if you are familiar with electrical diodes, if they're not light emitting, all they are one-way streets for electrical current. And this is exactly what that is. It's a one-way street. If I drive current this way, they will all fall through this energy difference and they will emit that light. So this could be, for example, a green or a red LED. But if I try to drive current this way, it will block. Okay? So here what I'm doing is I'm setting up a current such that these electrons, the flow of electrons is this way, basically on a conveyor belt like that, and each one of them is going to drop through this energy level difference and get pulled this way by the voltage. So I'm applying, just imagine applying a voltage here. I'm going to take electrons this way, they're going to drop that way, emit light, and go this way, and then I'm just going to put them back up here, pump them back up here. And basically this is how a laser works also. There's a few extra things to think about in terms of how do you get coherent light, how do you focus the beam, but those are fairly straightforward to deal with and not that big of a deal. So, so the light that comes out of this is the basic of this is called the PN junction. So what comes out of this is light that we can make be whatever wavelength we want, because we can, like I said, we can tune this energy level difference to whatever we want. All right, so this is known as a diode, or a light emitting diode, and the junction itself is called a junction diode. And therefore, if you wanted a transistor, all you got to do is put two of these together. So I've got two diodes, I've got two diodes basically back to back like this. And then all I do is I apply a small voltage to this thing here in order to control what its level is, and that determines how much current goes through. And I've made myself a really easy amplifier. Okay, so if I have another situation over here where I've got the other side, so this is now, for example, an NPN transistor. If I have an NPN transistor and I have a voltage across this level, if I'm trying to cram a current from left to right here, it can't go because it's blocked by this piece right here. But I can tune the size of this bump with a small voltage. So with a small input voltage, I can lower this thing, and all of a sudden I can get a huge current out because I'm driving a current. I'm trying to drive a current through this thing, and I can, for a small input voltage, pull this down such that that current can go, and that's called the gain of a transistor. Anyway, so that notwithstanding, that got a little bit out of what we were talking about, but essentially with the transistors, as you control this level with the voltage, it produces a very repeatable and clean response. And for those of you who like amplifying musical instruments, this is now what most amplifiers are based on, unless you go back and talk about a vacuum tube amplifier. But a vacuum tube is much less predictable when it gets to be fully saturated. So you can I forget now, I'm blanking on the name, but it's basically you can overvolt a vacuum tube and cause it to become distorted. And so many of the guitarists from past decades, like, for example, Jimi Hendrix, was a big fan of the distorted sound of the vacuum tube amplifier. And when it came to these things, it was just too clean of a sound, and it wasn't quite his thing. So it wasn't for that reason that he died, but I wonder if maybe he was thinking about that. Anyways, darn these transistor amplifiers. All right, so that's essentially the workings of the solid-state laser. All you got to do is take this light, make it coherent, and you've got yourself a laser. Alrighty. So let's start talking a little bit about radioactivity. We'll do a little bit of that, and we'll talk a little bit more about this. Well, we'll see how we go. I'm making predictions, but I don't know if they'll come true. We'll talk about radioactivity. We'll see how well we do today, and then if we're going to get into it more tomorrow as well. I would imagine we would. Okay. It's down at that point in the semester where you're picking topics that are related, and this is certainly one that takes special relativity and Einstein's famous equation of E equals mc squared, and some of the quantum mechanical stuff that we have been talking about, and kind of puts them together. So when a nucleus decays, that's a radioactive event. Radioactivity is basically the explosion of a nucleus. Now, just to give you a bit of perspective on the sizes of things that we're talking about. I think I mentioned this before, but the nucleus is incredibly tiny. Incredibly tiny. It is 100,000 times smaller than an atom. In other words, if you think about an atom and you say, well, an atom might be about the size of a nanometer or so, then the nucleus is that would be about what, 10 to the minus 9, right? And a nucleus is about 10 to the minus 14. Okay, so this is in the range of what's called the femtometer. When a nucleus explodes, it releases energy, just like any other explosion. It's not a lot of energy because, after all, it is just a small little tiny nucleus. But lots of these put together can release significant amounts of energy, as I'm sure you're probably aware. And when a nucleus explodes, it gives off what we call radiation. And just the detritus of an explosion, essentially. Okay, so radiation is what is thrown off by the explosion. Now, we have several different classes of radiation types, right? Radiation is emitted by the explosion, and it comes in different types. So there are characteristic types of radiation such that we classify elements that decay via what their main mode of radiation that they emit is. Okay? There are 3 of these, but by no means are they confined to only this. So for example, if we say this is a particular type of this emitter, that doesn't mean it never does anything else. It can often do other things. All right? So I just want to put that out there. There are 3 characteristic types, as well as the rest of the stuff that's emitted. Okay, this is only one piece of the radiation that might come out of a nuclear explosion. When a nucleus explodes, there's going to be a lot of stuff that's emitted. There's going to be, right? What's in a nucleus? Well, maybe we should talk about that first. Well, there could be bits of all of these things coming off. There could be large pieces, small pieces, pieces moving faster, pieces moving less fast. There could be electromagnetic radiation coming away. There could be lots of stuff. This is all characterized as radiation. But like I said, we have particular categories of what this is. So There are characteristic types, and then there are other types. So let's talk about this. What's in a nucleus, first of all? The nucleus, as first, now this might surprise you. I'm going to try and remember this. So the nucleus itself was first discovered in 1911. And it was a shock to everybody because it was well known that there was a particular particle that was fairly heavy. It's called an alpha particle, and it's actually one of these characteristic radiations. It's fairly heavy, and you could get the alpha particles, and you could shoot them at things, and it's fun. This is what a lot of the field of particle physics, experimental particle physics, does this. Nuclear physics, experimentally. Oh, it's just about shooting stuff and hitting stuff and see if you can blow it up. It's really great. Okay, so they first discovered it in 1911 because they were shooting these heavy alpha particles at gold, a thin gold foil, and found that some of them would hit and bounce off, which means that it was the momentum equivalent of throwing a baseball and hitting a car or a battleship or something, right? You're throwing the baseball and all of a sudden it's coming back this way. You're going like, whoa, what did that hit? Well, we have the ability to see the car or the battleship, but imagine that the mass of that thing was so crushed down and be itty bitty tiny thing that you had no idea it was there, and this thing hits and bounces off. So that was the big surprise for everybody in 1911. And then they decided to say, okay, what's the nucleus made out of? What's inside the nucleus? Is it made out of things? Turns out it is. It's made of different types of both charged electrically and not charged electrically particles. All right, so a nucleus is made out of a combination of these things. And you probably have heard of this. It's made of the protons. The protons have the positive charge. And the neutrons, which have zero charge. And if you know anything about electricity, then you'd know that like charges repel each other. So a nucleus with more than one proton in it is trying to explode, right? It's actively trying to get these protons to get away from each other, right? If I have 2, 5, 10, I could go up, we have 92 of these things, 94 of these things that occur. 94 protons. Could you imagine the amount of repulsion that this nucleus is feeling? It does not take very much for these protons to go, you know what? I'm out of here, right? I don't want to live in this kind of condition with all these other protons. They're all repelling me. They're so repulsive. I'm getting out of here, okay? So it doesn't take very much for this to happen, all right? Now, why do positive charges ultimately attract each other? This is a little bit slightly off topic, but not completely. Because there has to be something greater than the repulsion of the positive charges in order to keep this thing bound together. So these protons are bound together by a force that is stronger than the electromagnetic repulsion. And a force that's known as the strong nuclear force. Since they're bound together by a strong nuclear force, we just call it the strong nuclear force. Because, creativity. So, that same force acts on the neutrons. Neutrons also help space the protons out from one another so they don't get quite so angry at each other. Typically, there will be many more neutrons in a nucleus than there will protons. And when I say typically, I mean you have to get to the pretty heavy ones. For example, carbon is a typical example in which you have 6 and 6. Helium is this example where you have 2 and 2. So I say typically, but not all the time does it happen. that you have many more neutrons than you do protons. All right, so if you have a nucleus with the same number of protons in it, but different numbers of neutrons in it. So carbon, for example, can have 6 protons and 6 neutrons. Carbon can also have 6 protons and 8 neutrons. Of course, carbon has to have 6 protons, because if it had 7, it would have been nitrogen, and if it had 5, it would have been boron. So the 6 proton number is actually the thing that makes it carbon. The reason that it does that is because when it's electrically neutral, that means there's 6 electrons arranged around it in such a manner that chemically they act exactly as every other 6 electron carbon does, regardless of what's going on in the nucleus with the neutron number. Okay, so the neutrons, the extra neutrons being in there don't affect anything about the chemical aspects of the element. All right, it does affect the radioactivity of it, and ultimately the fate of what the nucleus might become. But chemically, it acts, carbon-14 acts just like carbon-12. So a nucleus with a same proton number but different numbers of neutrons. Okay, so here I have carbon. This is carbon, and it has 6 neutrons in it. And then I have this one over here, and this is carbon, but it has 8 neutrons in it. And my symbol for neutron is just N0. It's like N with superscript 0. That's what the no is here. Carbon, if it's carbon, we know it's got 6 protons, so I don't even need to really talk about how many protons something has. But here's a nucleus with the same number of protons and different numbers of neutrons. I just want to give you the word. This is isotope. These are isotopes. All right, so there's your vocabulary word of the day. It's a great Scrabble word, right? It's a 7-letter, and you can, if you get it right, you can fit it in many different places because there's such common letterings. I actually played this word against my grandmother, and she said, "That's not a word. There's no such word as isotopes." Isotope, like I had put it in a place where there's an S, so I had made it plural. So not only was it a 7-letter, I think I was on a double word score at the same time. And then she challenged me, and of course she lost. And that meant I got another turn. So I mean, it was a total destruction, which I think was probably the only time I ever beat anybody at Scrabble. Anyways, oops, I'm going to not erase that because this is characteristic type. So we're going to go back to that. So isotope, that means it's the same number of protons, it's the same element characteristics. Different neutron number means its mass is different. Okay, so that means that when I get a difference of 2 neutrons between these carbon atoms, I can separate these because one of them's a slightly heavier and one of them's ever so slightly lighter, and we can actually cause them to get away from each other through other means. Okay. Now, let's talk a little bit about this. Now, the 3 characteristic types of radiation that are emitted, they didn't know what they were at the beginning when they first discovered these, and so they just named them the first 3 letters of the Greek alphabet because the unknown was already taken. X. Right? X-rays had already been found, and they didn't know what they were, so they called them X-rays. And so they're saying, hey, let's call these X-rays, but you can't call them X-rays. And let's call them ABC, but that seems too pedestrian. So let's call them alpha, beta, and gamma. If you're unfamiliar, alpha is fish swimming, gamma is fish diving, and we go from there. We do know now what all these 3 radiations actually are. So radiation comes flying out of the nucleus? It must be because stuff was in the nucleus, right? Everything that's emitted by an explosion was in there at some point, right? Well, not necessarily, right? Part of the explosion might be that there was inside the exploding stuff, there was something that as the explosion was happening, this thing got caught up in the explosion and then got ejected. So it looks like it came from the explosion. So we have to, it did come from the explosion, but it looks like it came from the thing that exploded. So for example, you could imagine if there was, I can't come up with any good PC analogies for these things. All right, so let's imagine an explosion. What's something that explodes? I don't know. I can't come up with anything good. So I'm going to go with what I was thinking. I'm trying not to go with this, but I'm going to go with car bomb. So we're going with car bomb, and sorry, but it's like you have a car bomb and you say, okay, I've got the actual explosive here in this thing. It's a bunch of whatever explosive it is, and it's going to go off. All right, and we're going to detonate it from way over there. Okay, great. Now, how much of this actual stuff are you going to find? Probably not a whole lot of it. And also, the car itself wasn't part of the actual exploding material, right? The car is kind of subsequent to the explosion. Okay, so when the explosion happens and you go, wow, look at that tire goes flying off like this, and then there's a mirror that went flying off this way, and then the driver's seat's going this way, and there's the motor going that way. A car must have exploded. I mean, the car didn't explode, right? The car was exploded by something else. So, sorry, but think about that as we go through these, because not all of these are actual results of the thing that exploded. All right, here we go. Alpha here is a helium nucleus, and that means it contains 2 protons and 2 neutrons. And I'm going to abbreviate the proton and neutrons by using P plus for protons, right? This is P plus. Neutron is N0, and I think you can see why. This is a very tightly bound set here. They are very happy to be together this way. Now, naturally, the protons would like to get away from each other, but in terms of, okay, you've got to be near another proton, they're happy to do it this way, okay? So this is something that is basically the heaviest thing of all 3 of these, just of these 3 though. Okay, so this is the heaviest one, and it's known as the alpha. The alpha particles are the dump trucks of, or actually even better, they're the runaway trucks of the nuclear decay. In other words, if you've ever driven on the freeway and seen the runaway truck ramps, that every now and again, if you're on I-5, I know they have a couple of them north of Red Bluff or Reading, right in there. There's a bunch somewhere other, you see them. They're not frequent, but they're there. I think maybe there's one on 152 coming over the pass or near San Luis Reservoir. I don't recall. But wherever there's significant grades, typically there'll be a runaway truck ramp. So the alpha particle are the runaway trucks. They go in and they're going like, how do I stop? I can't stop. And so the runaway truck ramp is usually increasing thickness of gravels, kind of hopefully followed by a small upturn. And so they go into this thing and there's gravel flying everywhere and rocks and stone and stuff, and then they're making a huge mess and they plow into something to get them to stop, okay? That is what an alpha particle does when it goes through air or any other material that's made of, for example, molecules or atoms, right? It would do the exact same thing if it went through your body. It would leave a trail of detritus, right? There's a trail. What it does is it ionizes the air molecules. In other words,
An alpha particle that goes flying through air knocks into air molecules and pushes electrons off them, gives them enough energy to ionize electrons. So you end up with this trail of electrons and ions, which eventually will recombine, usually, unless you have a way to show, oh, look, this is where the trail is. Now, what happens is you can seed that trail with large numbers of droplets, and those droplets will begin forming really quickly right around the ions and the free radical, I guess that's what you call those things, free radicals and the electrons. So it will condense right in there, and that will leave a vapor trail. So essentially you can create the same situation that happens when, or the same result, I should say, that happens when a jet flies over and leaves a contrail. The contrail is not because of radioactive emission, it's just because of hot gas in a saturated atmosphere. Nonetheless, the same basic thing is happening in terms of leaving a trail, the physical mechanism being different. So these are the big heavy things. When you are hit with these, you have a big ionization trail that's left within you, and your chemistry in that area is going to be mixed up. So repeated hitting with these causes your body chemistry to become not smooth. It throws it out of whack. That's a technical term. And therefore you can become sick. So you could imagine getting radiation poisoning from a large number of alphas. You can also certainly die if you have a large number of alphas, but nonetheless. These are typically not good enough to get past your outer layer of skin. So even though you might be surrounded by alpha particles, you'd be safe typically just with the skin. Now that's different if the alphas were to be ingested. If you ingest an alpha source, the alphas then have absolutely no layer stopping them, okay? So our outer layer of skin is essentially dead. It's dead skin cells, and the alpha is so big and so slow that it can't get through those. And that's why the runaway truck ramp kind of thing, like it's hitting the air molecules going, and then it hits us and it kind of goes, stop it. Now, if you're on the inside, then you have no such protective layer, and therefore it's going to do a lot of damage. All right, so that's enough about the alpha. The beta comes in two forms, both the positive and the negative. So we have here the minus and the plus. Beta negative decay, that is an electron. And this is what I was talking about before. What gets caught up in the explosion? It may not be the actual stuff that's exploding. Reason being, electrons do not reside in the nucleus. We went through and I tried to motivate a little bit about an electron being confined to a small space that's about the size of even an atom. If you go down to even a nuclear size, the momentum uncertainty is so large that even if it was confined in there for a little bit of time, it won't be for very long. And it'll be gone doing something else. You cannot confine electrons within the nucleus. Okay, you say, well, what business does an electron have getting ejected when a nucleus decays? Well, so that's what I was talking about. It's not part of the actual stuff that exploded, but it is part of the ending radiation, the ending stuff that gets spewed out. How is it then? Well, you'd say, oh, maybe it's because it was in the vicinity and it got caught up in the explosion. Well, that's not 100% of an analogy. And remember, we're in modern physics here, so analogies of how things work in the classical world do not really translate into the quantum mechanical world. Nonetheless, we try our best. And it's for this reason that we get paid such large sums of money. Yeah, anyways. So where did this electron come from? Well, thanks to Einstein, we know that there's a large amount of energy that's released in a radioactive event, and some of that energy will get converted into mass. Essentially, Einstein's equation is telling us that there's an equivalence between the energy of a particle and the mass of the particle. So if I have enough energy in an ambient sense to create a particle, I can do it. Or, well, I can't do it, but it will do it. It'll do it for you. Likewise, I can also destroy matter and turn it into energy and have the mass gone. Now, that might come as a bit of a, oh yeah, okay. And then a little while later you go like, wait a second, that's not right. No, it is. The issue is that classically, we are always familiar with the concept of mass conservation, right? If you go to splitting a piece of wood because you want to burn it for fire, you'd say, okay, I'm going to take this big log and I'm going to chop it up into pieces. Okay, if you had weighed the log before you chopped it up into pieces and then you weighed all the pieces you chopped it up into, well, they should match, right? This is not a big issue, right? Ultimately, also, same thing when you burn it. But if I burn it, I weigh the piece that I'm burning and then I weigh the ash, they won't quite be the same, right? But if I catch all the smoke and I catch all the gas that comes off of it, then they would, right? Okay, but this is not that. This is not that. This is not just regular combustion. This is a situation in which we are creating particles. We are creating mass out of energy that is there. Because there's typically lots of energy emitted by the nucleus when it explodes, some of that energy may just spontaneously create the electron on the spot and eject it. So it's not quite like the example of the car bomb I gave you. It's more like a situation where something explodes and then something that you didn't expect to happen gets immediately created. And you can see there's no classical analogy to this really that I can think of off the top of my head. Anyways, there's the electron. It does just get created on the spot. It does not come out of the nucleus. I have unfortunately run into too many I don't want to, let me put it this way. More times than I care to remember in my career, have I run into people who have said, oh, a neutron, that's where the electron comes from. Because a proton plus an electron makes a neutron. A neutron is basically a bound state of a proton and electron. This is not true. That is in no way what is happening here. A proton and a neutron are similar, but it's not like a proton has an electron near it and you say, oh, now it's a neutron. This is absolute bunk, okay? So a neutron is not a bound state of a proton with an electron. No, it's not. And if any of you had that misinformation, please say goodbye to it. The electron is created on the spot by the energy that is available from the electromagnetic, from the explosion of the nucleus. All right. That being said, the positive part of the beta decay is the exact opposite of the electron, and does also have to do with this same Einstein equation here, in the sense that what I told you before was I can create I can create mass out of energy, okay? I can also do the opposite, which is I can create the energy out of the mass. So in other words, you kind of start thinking of mass as like frozen. I don't want to say frozen because I don't want you to think it's like actual temperature dependence, but there's energy wrapped up in the mass of things, okay? So if I take two masses and they are opposite to each other, they're opposite masses, I can cause them to hit each other, cease to be massive, and turn into complete energy alone, which means photons. Okay, so I usually would think of this as I take the two particles, I put them together, there's a flash of light, and the particles cease to exist, and the flash of light goes out. And so the energy that was wrapped up in these two masses is now in the flash of light. So the energy is still conserved, but instead of just saying it's only energy conservation, now it's really mass and energy conservation. Okay, so mass was never really conserved. Energy is, as far as we can tell, for most part, but the idea of putting mass under the energy umbrella needs to happen. Okay, so we have to have the conservation of things that have energy, and mass is something that has energy. So the other one here is known as the positive electron, which got contracted to positron, positive electron. And it is the anti-particle to the electron. In other words, this is antimatter. Sometimes people feel like, oh wow, antimatter, that's really, it's really rare. It's really, what's the word I'm trying to think of? I don't know, but it's rare. You don't come across it. It's uncommon. It's novel. It's a different thing. Well, yeah, because we don't really run into it every day. But nonetheless, it is around. We do have it. It does exist in the universe. It's not some fantastically crazy idea. I mean, maybe it kind of is. But it turns out that we can detect it, and it does exist, and it's in fact ejected by the same process as I just described. When there's enough energy to create a particle out of energy, sometimes it's the positron. Okay. So this is the antimatter electron. If I take a positron and I put an electron near it, you'd see right away that from their electric charges they will attract. However, when they hit each other, they will cease to be matter particles, and they will now be photons, and off they go. All right. This is the antimatter electron. Last one here is the gamma, which is just the high energy X-ray. It's essentially electromagnetic radiation. It's an X-ray, just higher in energy, right? If you look at the spectrum, the gamma is usually the one on the very end. And it has the highest energy and the shortest wavelength and all that great stuff. But it is electromagnetic, meaning it is carrying zero electric charge. It is traveling at light speed and can basically go right through almost everything because it's got such a large amount of energy. In terms of ionizing, I mentioned the alpha as being the biggest ionizer. It's the dump truck, right? The runaway dump truck. The gamma is not as big of an ionizer because once it's absorbed, it deposits all its energy right there. Whereas this one, right, it goes on the runaway truck ramp and scatters all the gravel, right? It's like it creates all these ion trails, dust cloud, all the stuff behind it. It leaves a big trail, and that's a trail of ionization, and that's the thing that messes you up. So if you had to, you'd say, if I have to swallow one of these, I'm going to swallow the gamma emitter. Because the gamma emitter could be outside me or it could be inside me, and it's not really going to matter. If it's outside and the gamma can go through me, it's going to do that. If it's inside, the gamma can go through me and it's going to do that. If it's outside, it can go in and then hit something. If it's in, it could hit something. It doesn't matter. You can't do anything except have large, thick sheets of lead to try and protect you from the gammas. You might as well swallow that one. If you had to swallow if you had a choice, you'd take that one to swallow. So next time you're in a situation like that, where you're being forced to choose, you have to swallow one of these or we'll do something bad. I don't know. Wait. I guess there you go. Okay, so these are the characteristic types. Let's talk about what happens. Let's first examine a very basic nuclear explosion. Let's examine the nuclear decay in which the let's examine a nuclear decay in which it's not so destructive. There are several classes of how badly does the nucleus explode. Sometimes the nucleus explodes and gives off just one of these, and that's it, and then the rest of the nucleus is still there. Sometimes it's this huge thing where the nucleus is right, it's giving off this and this and that and this and that, right? It's a terribly catastrophic event for the nucleus and for those around it. But let's first concentrate on just the easiest possible one, in which let's make the assumption that we start with a nucleus, it decays via one of these only, and that's it. And it becomes something else, right? The nucleus then becomes something else, and we're questioning, what is it that we're left with? Okay, let's suppose that we have a situation where simple decay, simple radioactive decay, in which we have what's known as a parent nucleus, and we have well, it's called the daughter nucleus. I don't know why they chose daughter rather than son or just offspring, but nowadays it's called the parent and daughter nuclei. In past years, it's been called the mother and daughter. Is that right? I guess it's kind of like the original one gives birth to the other one. So it kind of makes sense with the mother. I don't know why the daughter, though. Anyway, simple radioactive decay, that we start with a single element. We start with a single species, okay? Single element, single radioactive element. And we just imagine that it ejects one of these, only one of these. Decays via one of the three types. And then, and that's it. It doesn't explode and emit anything else, just one of those. So I'm going to say that it's still intact. After it spits out, say it spits out an alpha, everything else is still together. I mean, it's the leftover thing is still intact. Okay. So let's start with something easy. I'm in a room which does not have a periodic table because I'm not in my normal classroom. I'm in one of the computer science rooms. And of course, they don't care about stuff like this, so there's no periodic table around, but there are all these posters about how to make security architecture or a career in network engineering. And all this crap that nobody cares about. Well, some of you probably do. And ultimately, I guess we all do. So thank you to the computer people for making our world all secure or not, whatever. Let's start with a heavy nucleus because ultimately we need to decay. It needs to become something lighter, usually. So let's start with something like uranium. Let's assume our parent nucleus is uranium. And let me show you how to write this. Uranium, the symbol is U. And there are basically two numbers with which we associate uranium, and one of those is the proton number. And of course it's the proton number, because if it wasn't that, then it wouldn't be uranium. So the proton number is 92. We don't typically always write the proton number because the element takes care of that. So sometimes you'll see this with written with a 92 here. I think it's there, or maybe it's on the other side or something like that. It's usually down there somewhere. However, on the top side of this is the slightly more important number, and it's one that's not completely helpful, but it's usually the one that everybody talks about, and that is the total number of protons plus neutrons in the nucleus. This is called the, let's see, this would be the atomic number, because that determines the atom. So this is probably something like the mass number. I don't know, whatever the chemist people call it. It's the total number of all protons and neutrons in the nucleus. And so let's say that this is 238. And so I will call these out individually. This is the element symbol. And the element symbol, as I said, correlates directly with the proton number. And the reason it corresponds directly with the proton number is because of a fellow by the name of Henry Moseley. Moseley was the one who essentially built and finished the periodic table in the way that we have it today, and ordered it so that it is in the correct ordering. He was the one who realized that it's by proton number that we order the elements. So just to let you know, Henry Moseley, there's a guy who back in the prior to 1920, so this would be about 1915 to 1918, 1917, he was killed in World War I, which is one of the great tragedies of science, but nonetheless, he was the one who really gave us the periodic table as we know it. This is the total number of protons plus neutrons in the nucleus. And I think it's usually labeled as A because it's all, or it's the opposite of Z, which is the proton number. I don't know why Z is the proton number. Let's take a look at what happens to an atom of uranium as it undergoes all three of these different types that I'm currently erasing. If it undergoes each one of these types of decays. All right, so let's start with alpha. What this means, and of course, you know, I'm going to draw this picture. So here's your uranium. And what happens is it becomes this other element here, which I'll just call X, plus an alpha particle. And the alpha particle is shooting away like this. Okay, so the uranium is here sitting, essentially we can consider it at rest, and all it's doing is spitting out an alpha particle this way. And of course this uranium, this leftover X particle here is going to be recoiling due to momentum conservation. We won't worry too much about that. Our question is, what is the X particle? Find X. We would write this then as something like this, where alpha we know is a helium, so it would be this. Helium-4. So we could write it like that. And therefore we could just kind of subtract and find out what the X is. All right. Now, one thing we could do is right away we can look at what the total number of neutrons plus protons is going to be. And you can see that I had 230. Sorry. Wrong isotope. Okay. The reason is because I like blowing things up, and that's because 235 is the isotope that blows things up, and 238 doesn't. Nonetheless, we can look and see what the isotope of X is going to have in terms of total protons plus neutrons in it. And that's going to be 238 minus 4, because they're still there, right? It turns out that you have to conserve the number of protons plus neutrons, right? So on this side, the number of protons plus neutrons is going to equal the number of protons plus neutrons on this side. That means that this thing should be 234. Right here. The question then is, what would the proton number be? And therefore, if I figured out the proton number, I'd be able to tell you what the symbol is instead of using it as X. What is the symbol? So in this case, we know that there are 2 protons in the helium nucleus, and there's 92 here in the uranium, and that would mean that I have 90 left over here.
So, once I realize that there are 90 protons left out of the 234 total things in the nucleus, I am free and clear to assign thorium to this element here. And that means I can write this as 234 thorium. And that
is what element X is. Alrighty. So that's what happens with alpha decay. Alpha decay is, I would say, fairly straightforward. What it does is it moves you two places back, two places to the left on the periodic table. Okay. There is a limit to which elements can emit alpha particles. For example, a helium atom cannot emit an alpha particle. It already is one.
And incidentally, you might say, well, I don't know, what might you say? But you might say, you might ask, what happens to this helium? This helium nucleus that's emitted is dangerous. I've just told you that if you swallowed them, you could get poisoned by it, right? But
people swallow or they inhale helium all the time, right? So what's the difference between inhaling helium as a gas and inhaling these things? Which, by the way, you wouldn't want to do that. The difference is that these are still moving relatively quickly and do not have electrons associated with them. As soon as they ionize and bop into enough air molecules, they eventually slow down. They grab two of the electrons that they just pushed off a couple of the air molecules, and it becomes an atom of helium gas. Helium gas is completely inert. It is totally harmless to us. We can, in fact, inhale it with no repercussions other than sounding like Donald Duck or something like that. So the existence of helium on Earth is entirely due to this process. We do not have helium on Earth otherwise. It is completely due to radioactive decay. And every time you inhale it, that's because it used to be something that was dangerous, but now it's not. And the same thing when you put it in a balloon. It used to be a product of, it is a product of radioactive decay. It's just not dangerous anymore. Okay? It's like the fire. The fire's gone out. So there's nothing here that's going to burn you anymore, right? Or something like that. We don't have helium in the atmosphere. So all balloons are inflated by products of radioactive decay. So alpha decay moves you two spaces to the left on the periodic table. What about beta decay? Let's look at beta decay. If it beta decays, what effectively happens is, let's go over here. What effectively happens is that, and this is where this misconception comes in. Let's first talk about beta minus decay. This is the situation where my uranium-238 goes into some X thing here and ejects an electron. Electron comes out. How does an electron come out?
Remember, it was spontaneously created
On the spot, outside the nucleus, and is now flying away. It was not part of the nucleus to begin with. How does this happen? Well, what happens is a proton actually decays. Protons, it turns out, are not stable. Neutrons. I'm sorry, I got that backwards. Neutrons are not stable particles. Neutrons can decay. So the reaction that happens inside the nucleus is that a neutron, an N0, has become a proton plus an electron. And then there's something else in here just to make energy conservation work out right. It's called the antineutrino. We're not going to talk any more about that. but nonetheless, this is the situation of a neutron becoming a proton. So what's the effect here? If I look at the number of neutrons plus protons in the nucleus, that should not change. That should be 238 to 238 because this is not a proton or a neutron, so these two numbers have to match up. However, I did change the element because now I've got one extra proton in here. So in this case, this element must be 238, and it must be 93 now instead of 92, because I lost one neutron and I gained one proton. So this has pushed me to the right one spot on the periodic table. And that must mean that I'm at Neptunium for the element.
Beta positive decay is the exact same thing, run in reverse. Beta positive decay
Is the situation in which the positron is ejected, and instead of a neutron becoming a proton, it's a proton becoming a neutron. This is what I was meaning to say in the first place. Proton becoming a neutron plus a positron plus a neutrino. Okay. That means I've lost one proton in this example, and that means instead of having uranium, now I will have moved down one space on the periodic table. Okay, so instead of being uranium now, I draw the exact same picture with a proton ejected, with a positron ejected, and now we get X, which is equal to 238 still, but it's number 91. What's number 91? It must be, so it's thorium,
I forget what number 91 is.
oh well, it's whatever this is. I'm just gonna leave that as a question mark. I mean that I know and you should also know. No, I don't know, that's not true. All right, last one before we wrap up is the gamma decay. The gamma decay here looks like this. A gamma is just electromagnetic radiation, and therefore it does not change the number of the proton or neutron or the element at all. What it's doing is it's causing the nucleus to decay from a higher energy state to a lower energy state. Just like an electron would drop from a higher energy state to a lower energy state and emit a photon, that's exactly what's happening. It's just that the photon is so high energy because these are nuclear states. They are separated by huge amounts. The ladder rungs are really very far apart from one another. So this is just a way for the nucleus to get rid of excess energy. All right, so in this case, this would be U. And that means I would usually put a star on that one to indicate it has excess energy. It's in an excited state. It has that energy that it can get rid of. All right, well, those are the three types of decay and what they do. We'll pick up with a little bit more of this tomorrow and finish off, do a little bit of review, and that'll be that. So I bid you good day, folks. Happy rest of your day. See you later.